So welcome again to the 13th lecture here in the new year, or almost the new year, depending on when you watch this video, on energy and finance. And today we're going to discuss regulated investments. So particularly we're going to have a look at the paper by Dobbs from 2004. So what the outline will be for today will be first we'll have a recap of the model by Pindyck that we did before the Christmas break, which was a monopoly investment in capacity, so gradual investment in continuous investment in capacity. Then I'll briefly discuss what regulation amounts to in the energy world, so I have a brief look at energy networks. The next part I'm going to have a look at, if you're a benevolent regulator and you would like to optimize welfare rather than optimize profits, which the monopolists will do, how would you then expand the capacity of this network? So we're going to have a look at Pindyck's model, but now with as our objectives maximizing welfare rather than profits. And then finally we have a look at the behavior of a monopolist. So a monopolist again optimizes its profits, but now regulated by some regulator, and this regulator is going to apply a price cap. So that's a maximum on the price that this monopolist might set. So let's then first have a look at this recap at Pindyck's model. Remember, we have this monopolist which could expand its total capacity. What this monopolist was going to do is to maximize its profits. So it's going to expand capacity as total demand grows, but in this model actually both capacity and price are both endogenous. So they are both choices that are chosen by the monopolist in order to maximize its profits. And there's of course this connection between capacity and price in the form of the demand equation. So demand is given by inverse demand rather. The price is a function of total output, k to the power minus gamma, where gamma is a positive number but smaller than 1. That's the elasticity, or actually the inverse elasticity of this demand function. But all of this is multiplied by this parameter theta, which is going to be the uncertain parameter. So we might refer to this as the size of the total demand. So this theta parameter is exogenous, and it moves actually according to our favorite stochastic process, geometric Brownian motion. So d theta equals drift times theta dt mu plus the volatility sigma times theta times dz, the Brownian motion increment. So we'll have these investments. So this firm can invest, expanding its capacity, so adding some k to its stock of k that it already has. But of course there's going to be a cost of doing so. This is going to be the investment cost, and it's going to be I per unit of capacity investment. And again, for convenience here, we just assume that the marginal cost of producing the good here, so once you have the capacity, you incur no further marginal costs of making any goods. So C, if you wish, is going to be equal to 0. No marginal cost, just marginal cost of investment, but no marginal costs of production. So what we saw there was when we have are at some given capacity, say we're at this point on the horizontal line, so it corresponds to a particular value of total capacity that's available to us. What's going to happen? Well, this demand theta is going to move up and down, up and down, and it will be moving in this picture, also moving up and down in this graph, because k remains constant until this demand grows so high that we reach this particular boundary here, which is called theta star, which depends on k. So this boundary is actually increasing in k. So what happens when theta reaches that boundary or passes that threshold? Well, at that point it's going to be optimal for this monopolist to invest in new capacity, so to move a little bit to the right in the picture, which gives us basically some more breathing space to have further expansion of this demand parameter theta until we make the next investment in capacity. So in this region below this curve, so in this region over here, of course we have this value function for the monopolist. Total value of the function, we can write this, so it's going to depend on both these parameters. So how high is theta and how much capacity do we have, k. It's a function of theta and of k. That's our value. This description is valid in this region only, so as long as theta is below this curve, below theta star k. As long as that's the case, we have no investment, so k remains constant. So in that weighting regime, this w is going to satisfy our Bellman equation. So it's r times this w is going to equal the profit flow at that point. How much is that? Well, it's essentially the revenues that we get, right? So it's a price times the quantity that you output. So the output quantity is k, total capacity, and the price is theta times k to the minus gamma. So if you multiply those two together, you get this particular expression for the profit flow, theta times k to the power 1 minus gamma. And then we have our other two well-known terms here. And of course, these only depend on derivatives of theta, of w to theta. So you can figure out what the general solution to this Bellman equation is, and it takes this form that we now know pretty well, I guess. So this profit flow is linear in theta, so it's theta times something. So it takes actually the form of a growing perpetuity, so we know where that value should be. So it's this theta times this constant k to the minus 1 minus gamma divided by r minus mu. So this first part is actually the growing perpetuity of all the income that we get from now until infinity from the capacity k that we have already available for us today, the k that we have. And then secondly, there's going to be this term which represents the option value of further expansion of capacity, which is has this form proportional to theta to the power beta 1. So of course, why beta 1? Well, this description is valid in this part of the domain below this curve. So theta equals 0 is actually part of this domain. That's over here. That's the x-axis, if you know, the k-axis, if you wish. But it's of course it ends over here. So theta is not going to infinity. That's outside of that domain. But we do have to worry about this end, this boundary of the domain at 0. So there we don't want option value to blow up to infinity. So we have to discard, as before, the negative power, the theta to the power beta 2, because that would go to infinity as theta goes to 0. We don't want that, but we can afford to have this beta 1, this positive power over here. And we multiply that, of course, by a constant a, but here we have a coefficient k, but this coefficient actually will be different depending on the value of capacity that we already have. So in a sense, this coefficient itself is again a function of capacity k. So together this second term here is the option value. So I call that f before. So f is again a function of theta and k. So now we also have to impose those boundary conditions at the investment threshold, so at theta star k. And we saw that the value matching condition here amounts to saying that the marginal value of w, so the w dk, so the marginal value of new investment, should equal the investment cost I at that point. So that's the equivalent of our value matching condition here. And we also want to have optimality, so we also have smooth pasting, and that basically is the theta derivative of that condition. Now we can get on with solving, particularly for this theta star k, because we can now plug in what we know is the expression for w. So it's this function that we just saw on the previous slide. It's a function of theta and k, and we can take the k derivative, and we can also take the second derivative here, this mixed second derivative, plug that in, and then solve the two equations that you have. And those two equations are written here. So this first value matching equation says, well, the derivative with respect to k, so we used to have k to the power 1 minus gamma, so taking the k derivative, the partial derivative, brings down this 1 minus gamma and reduces this power here to minus gamma, so reduce it by 1. And of course the k derivative of the second term here introduces this k derivative of this a coefficient. So A prime of k is the derivative of A of k. So that's value matching, and of course a similar computation gives us the theta derivative, the smooth spacing condition. So now we can actually go on and solve for these two equations for theta star, and the convenient way of doing that again is multiplying the first equation by beta 1, multiplying the second equation by theta star, and if we do so, well, then the second terms here are going to be the same, and that then allows us to eliminate those, and we get an expression for theta star as a function of k, and it turns out to be actually pretty useful to actually write this as theta star is function of k times k to the power minus gamma, because that thing is going to be a constant. So all these things on the right hand side here are just the parameters of the model, so the r and the mu, the drift, the gamma, this elasticity, inverse elasticity, and the beta 1, which depends on the r, mu, and sigma at I, or constants of the model. So this theta star times k to the minus gamma is going to be a constant, so it doesn't matter what k is, this theta star times k to the minus gamma is always the same. And actually this thing actually has an interpretation, because it is, as you can see, it's exactly the price. So theta times k to the minus gamma was price. So at theta star, this is going to be the price level at which new investment is going to take place, because we have reached the theta threshold. So in the picture, this looked like this. So this yellowish line was this theta, which moves according to GBM, geometrical Brownian motion. And each time theta increases beyond its previous maximum, we are going to expand. We reach a threshold essentially, and we are going to expand capacity. And what you can see as well is that at those points exactly, the price is reaching this threshold level, which I just computed, which is the black dashed line. So the blue price line reaches the black dashed line whenever theta reaches the threshold, depending on the k that's available at that point. So that's Van Dijk's model, the recap of that. So we saw that before, so now we're going to work from that to actually have a look at regulation.